Today we're going to talk about doing cardinality estimates using HLL in Go. It's about a small utility that I wrote on top of an HLL library that are already open source. I'll talk about what is HLL a little later. HLL stands for HyperLog log. It's one of the estimation algorithms used for large data sets. So the goal here is to analyze something like how many unique visitors do I have my site have yesterday, or how many unique visitors does my site have last week. It could be data that is stored in a database or data that's stored in plain text files. Normally, to do this stuff, you have to take all of the data and do a count distinct. You have to unique all the data in there. So let's talk about accurate but slow solutions. You might have a DB, and you would run select count distinct from events where date is between X and Y. You might have the data in a file, so you would do cut to sort to unique to WC or to awk, and you will get the data there. So let's see how we do this without HLL. Let's say I have a sample data set. I took 2 hours of our data, and then it's about 92 billion rows and across 4,000 files. So it's about 75 gig of data. In reality, we don't need to distinct all of the data. We can extract only the columns that we need. If we want to group by one column and find unique surfers, so it'll really be only 2 gig of data we need to sort. But there's a process of extracting 2 gig from the 75 gig. And the sample data is in the first line over there. It's the first column is the event type, and the second is the visitor ID. So let's do it for real. So we can calculate I have a find line which finds all the files, then I pass it through GNU parallel, and pass it through cut, through sort, through awk. Finally, I get the estimates in about 1 minute and 50 seconds. Now let's talk about doing this without with an estimate. So HyperLog log plus is the algorithm. It started off as log, and as a French researcher named Fijolet who made HyperLog log, and then some Google researchers who made some improvements to that, and they call it HyperLog log plus. I hope it doesn't get longer with more improvements. So the good thing about HLL is that you can do unions, which means that if you have a large data set, you can actually break it up into smaller chunks and do the calculations separately and merge the results. So you can use it in a MapReduce style job where you can say you are still scanning all the data, but you can actually do it parallel and join the results. So you avoid the sort in the end. You can also do it in incremental update style. So if you are maintaining hourly uniques or daily uniques, and you can save it every day, and at the end of the week, you can actually run an estimate across all of the data. So the way you use it is dependent on how your application is. I have a small command line utility called dice. The reason it's called dice is that I actually made 2 programs. One was called slice, the other one was called dice. So slice and dice. Slice was a replacement for the Unix cut, which was it's like 2 to 3x faster. It's pure Go, but we don't talk about that right now. So dice is a utility that does the SLL. I only have written like 150 lines of code that wraps an open source library. So I'm really talking about somebody else's library. So let's do the same thing with the dice. So I have the exact same thing, except you can see that one of the invocations of dice is inside the parallel call, which means that that step is done in parallel, and then I run through the regular dice. So I get pretty much the same results in 22 seconds. So that's 5 times faster. Now, this is just a demo, so it's 5 times faster for this use case. In reality, you might be calculating many of the steps ahead of time, maybe a day before that. So it's depends on your application. It could be 1,000 times faster. But if you look at the results, I have T5 is 31 million, but in reality, it is 30 million. So it could be off by 1% or 0.3. 0.1% or something is we naturally see in our data, but it could be up to 1% off. There are cases when I have tried this thing on a Hive MapReduce to Hive stream through this one, and I've got like 50% off. So I still haven't figured out why that is the case. But why is it so fast? In the previous task, there's a little bit of cheating in getting 22 seconds there. In the previous task, only the extraction of the file was in parallel. Sorry. In this step, the extraction of the cut was done in parallel. So the file read is parallel, but sort was done in a single thread. Whereas in this one, the HLL portion is also done parallel. So that's also why it's 5 times faster. It used more cores in the machines. So you can see in the timeline here, the real time is 22 seconds, but the user time is 4 minutes, 45 seconds. Usually says you use more CPUs at the same time. So how does HLL work? 1 minute, 30 seconds, OK. How does HLL work? So in a random stream of integers, 50% of the integers start with 1, 50% start with 0. That's clear. 25% start with 0, 1. 12.5% start with 0, 0, 1. It means that if you observe a random stream of numbers and stop at if you see 0, 0, 1 is the highest sequence, it will likely have a cardinality of 8. A real HLL algorithm does a lot more than that. They actually divide the 64-bit. Yeah, so the HLL library that I'm using is from a company in Portland, Elytics. They have an open source library, and then that's it. Ready.